This is Computing Up, conversations about computation writ large with Michael Littman and Dave Ackley. This episode was recorded July 18th, 2023.
Hey, Dave, how are things going in Albuquerque?
As far as I can tell, pretty good. Where are you at now?
I am at the moment in Alexandria, Virginia, and this is now the end of the government fiscal year. So we're doing closeout, which means all the proposals at the National Science Foundation that are going to get funded need to get funded right now. And so I have this giant stack, a virtual stack of proposals to sign off on. And it's been, nonstop, not a lot of sleeping.
Well, if you have any extra, you can sign them off on all of them, or you just have to throw them down the stairs and only the top step gets signed.
No. I have to sign every single one of them. There's there's 100 or so left in the stack right now, and I expect a pile more on Monday. But those are basically the program officers do their darndest or program directors do their darndest to make recommendations. And then I just have to look it over and be like, yeah, it's fine. I don't really get to me. I don't really make the decision, but I do have to approve it. But I am the last approval. Like after that, nobody above me gets. I guess they can probably overrule it in the sense that they could fire me or something or change the money flow. But I'm the last official approval.
All right. Well, so then you get to go right at the end of the fiscal year. I guess that's the story.
Yeah. Yeah, and so we teeter between like we've got money left over, we should spend it, and oh my gosh, we have zero money, we're going to go into debt, and like just finding that balance and then click when the door closes, it needs to be at zero. I think we'll do it.
One of our grants way back when was one of those ones that got turned down, and then all of a sudden it got turned back up again. Right at
there was
the
a
end
little
of the
pocket
year.
of money.
Yeah. Anyway,
it's very satisfying. And the other thing that's going on is there's a tremendous amount of interest at like the executive level, like the president's office, about AI at the moment. And so there's been a bunch of presentations to senators and presentations to the president's been talking to the companies about AI in various ways.
Some companies.
Yeah, a handful. So maybe we should kind of transition into interview mode. Smooth, right? So today we're going to have on Jonathan Frankle, who is the chief scientist at Mosaic ML, and he's going to tell us.
Actually, he is no longer the chief scientist at Mosaic ML. He is now the chief scientist neural networks at Databricks.
There we go, and that's really interesting because the thing that I knew not to read was assistant professor of computer science at Harvard, and we can talk about that as well. But I met Jonathan through my graduate student and Jonathan's advisor, Michael Carbon. And Jonathan and Michael and some other folks did just an amazing piece of work on neural network pruning. And we had Michael Carbon on the show to talk about it. And a couple of months ago, Jonathan and I met for lunch, and we had such a cool talk that I was super sad when it was over that we didn't record it and share it. But then I had a great idea, which is like, oh, well, maybe Dave could have the conversation, and this time we'll actually remember to record it.
All righty.
So let's do that. So yeah, Jonathan, it seems like you've been I was looking for your bio. I saw you've done a bunch of podcasts recently. How has all this been? How is this, transition of roles and so forth? How's that going for you?
It's been completely insane. So to give context for anyone who's listening, I was chief scientist at this little startup called Mosaic ML. I can tell you more about Mosaic in a minute, but we got bought by a much bigger startup called Databricks a couple of weeks ago. And so now instead of being a 60-person company, I'm now part of a 6,000-person company. And I have a lot of amazing new colleagues, every single one of whom wants to meet this week, or I guess now last week. So it's been a little busy and a little crazy. And I'm looking forward to catching up on some sleep, getting out to ICML and enjoying the island for a little bit. In the meantime, getting acquired doesn't mean the work stops. It means the work goes into overdrive. And now I have higher expectations of some folks who paid a lot of money for the chance for me to, go and do bigger things. A lot of very eager colleagues and very eager salespeople. And it feels like, everything just turned up several notches. Wow. Not that I'm going to go and just lounge on the beach for the next while.
Now, and the can you say what the rough dollar figure was that they acquired your startup for?
The amount that's reported is about 1.3 billion.
Right. So that's That is an unimaginably huge number. So
it is, although it looks small in the grand scheme of what's going on in AI. So take your pick right now, and we can chat about the economics of the situation in a little bit. But we're hearing 50 billion tossed around for OpenAI's valuation and things like that. So we're,
oh wow.
it's nice to have a successful exit. We're still a small fish in the grand scheme of things, and it's good to always keep that in mind. I remind my team about that a lot. We got acquired, but we're still a small fish, and we still got a lot of work to do to start swimming with the bigger fish.
So can you give us the elevator pitch for Mosaic ML's tech? What was worth 1.3 in addition to the engineers?
So, this was I asked about this when they first reached out to us and wanted to have the conversation. Is this just an acqui-hire of my research team? And the answer was no. We want your product, we want your brand, we want your people, and we want your sales pipeline. So
the whole thing.
Everything.
So they want
also
everything.
Your firstborn child and what you had for lunch last Thursday
and the next 4 years of my life.
Yeah.
But they no. So at Mosaic ML, what we did, or what we continue to do, because the product and the brand are sticking around, we're just going bigger. We train large scale neural networks for contract. I think that's the way to think about it. You want a custom chat GPT style model? Call us. So
Okay.
a lot of the labs are building, building one big model, you're building the Saturn V, you're building one monolithic thing that needs to get you to the moon once and back safely. I think of us as more kind of the SpaceXs of the world. We want to get into space and get into space repeatably and reusably and do it over and over and over again in the most boring way possible. So anybody can come to us and say, I will take one 30 billion parameter language model, please. And I will say, please provide your data set and please book a time on our cluster. And I will see you in 30 days. And things come out right the first time.
So that's fascinating. Let me ask, because I'm not following this stuff too closely, so I'm going to say things that are probably a little dim. But so I've just recently learned about this acronym LoRa, LORA, which apparently stands for Low Rank Adaptation. And is that the sort of thing that Mosaic ML is doing in order to turn around these?
No.
No,
we train from scratch.
So you make a new model, 30 billion numbers are changing for each contract.
Yeah, from the beginning. We have our own in-house models that people can build on if they want a running start. But there's this funny thing. First of all, a lot of people do need to pre-train their own models. Think a company that's building a protein model. Building on an open source llama style model is not going to be very helpful.
Shakespeare doesn't help with that.
It turns out Shakespeare didn't know much about biology at that time, at least not biology as we think of it today. And then I've got customers who they're designing a Korean language model, and so having all these tokens dedicated to other languages or dedicated to English or math or programming, not very important to them. And they want something different. And everybody seems to kind of, when it comes down to it, there is a different model for everyone, and there's a lot of value in customizing.
Well, so Jonathan, I recently read an article that oh boy, I think it was in Education Week. So this is basically a publication that talks about education, and in particular, the writer was talking about tech education, and how the existing language models do a lot of weird things that make them inappropriate for use in classrooms. But this education group was about to create a new language model that was only with, approved educationally appropriate materials and so forth. And I said to myself, and maybe to some other people, that's not possible. We don't have the ability to do that. We can't train new language models. They must be just fine-tuning on this new data. You're telling me that's not true?
Honestly, it's not that hard. It took an enormous amount of work to build the infrastructure. We're a 60-person company, and I think 50 plus of us are technical people with their hands on keyboard building this stuff, all the way from low-level systems and orchestration and GPU failure handling, all the way up to modeling and science, and every level of the stack in between. But yeah, we can just turn around models now. Our friends at Replit, this is my favorite example. They came to us. I think they had been working with us a little bit, but 10 days before they had a big developer conference this spring, they said, we want our own custom in-house code model that we can use for autocomplete on our platform. So they had 10 days, they came to us, and 3 days later they had the model. And they had a week to go and play with it and fine tune it and do a bunch of other cool stuff on it. That's the kind of reliability I want.
So does that mean that you're using like the kind of stuff we talked to Michael Carbon about sparsification and that kind of thing. You're just doing it brute force. I mean, I thought people would talk about, it costs $1 million in electricity and the power of Iceland.
How much does it cost?
So forth to train a model these days.
Tell me what it costs. What does it cost? Tell me what you think it costs to get to GPT-3 quality. I love quizzing people on this.
I don't know. I thought people was like $1 million just in electricity.
10 million.
So it's fun to do the math on this. I really like to get into the hard numbers. Our list price for this is about 800,000. Depending on circumstance and what you really want from it, it's probably anywhere from 300 to 800,000. Electricity is negligible, actually, as a cost. It is all the GPUs.
The hardware is but that's sunk.
It's sunk, but you're amortizing it over 3 to 5 years. And when you're buying, $30,000 per accelerator to $50,000 per accelerator, you're getting 256 of those for one of the clusters I play with. It becomes a huge expense, and you're really just paying for the compute time on that, plus our software on top of that to make it easy.
Sure. So okay, well then. That's interesting.
But here's the other.
What were these people talking about? Where people were giving me the impression that OpenAI and all these things, that these guys had this gigantic moat because just to train a foundation model was such a huge investment that everybody else was going to be stuck using it rather than doing their own. And you're saying that's out the ass.
That's the story OpenAI is telling to the public and to the government and to the president, and to the NSF for that matter. And honestly, I don't think that's the real story. There are a lot of companies out there that can train these models. We're not the only ones. A lot of companies are training them for internal use.
Right, but to me, the point is, it's just, again, except for hardware costs, it's not that expensive. It's a few days and a few hundred super GPUs.
Yeah, if someone came to me today and said, I want GPT-3, not GPT-4, but let's start with GPT-3, I would tell them it's probably about 30 days on one of my H100 clusters. So call me when you're ready to go. Now, I never tell someone to actually go and train that model first. I want to see you train a small one and make sure that, basically I want to make sure that when we shoot our shot, we hit the target.
You don't want to burn 30 days. But to me, there's two sides of it. There's basically, there's the compute, obviously, and you're telling us about that. But I would think that if you want to train a large language model, you need a lot of vetted data. And one of the problems that they're having is that they're just throwing everything, including the kitchen sink, into the data sets to train on, because if they don't, then they don't have enough data. What can a smaller, a Korean group or an education group, like, how much data do they actually need before they can get something that you can have a conversation with?
So you still need in the order of billions of tokens, but it depends on how you get there. So we can go to hard numbers. How many tokens do you think all of Wikipedia in English is? Give me a guess here.
100 million.
10 billion.
It's about 4 billion. So, Price is Right, rules. Dave, you win. So you get
because I went over.
you get the vacation to Hawaii.
I was closer, but okay.
So it's about 4 billion tokens. I need to get to 1 trillion tokens if I really wanted to train like a good quality 30 billion parameter model. But as you start adding things up, like, you get to interesting places. There's a great data set called Pesto put out by the Allen Institute recently. It's open access scientific papers. That's about 80 billion tokens, if I recall correctly. So you start things that up. There's this great data set called The Stack that was put out by some folks at ServiceNow and Hugging Face earlier this spring. It's permissively licensed GitHub code, filtered, separated by language. You can pick whatever subsets you want. The subset that I picked of, what I thought was the most reasonable languages, several hundred billion tokens. So you start adding this up, and you end up getting to a pretty good place. Like, there's a baseline of, between, let's call it 100 billion and 500 billion tokens that, if someone was coming in, that's kind of your foundation. And then you start mixing in all of your domain specific data. If you've got your Korean language data. Awesome. Let's mix that in. But people are probably going to want a little English out of the model anyway. But we can put in Korean language Wikipedia. We have the Korean subset of web scrape data. So, at Mosaic, we have a data team, and they spend a lot of their time cleaning up this public open access data, producing kind of internal versions of it. And those are available to our customers. And eventually I'll figure out how to open source them properly. But it turns out that having an S3 bucket open to the web means you end up spending a lot of money in egress costs for your users. So I need to find the right place to put them. But We want to share this data, but we spend a lot of time, getting this in clean, good shapes that our customers have a menu and they can kind of pick, well, I don't want to touch this one, but I do like that kind of data.
So instead of saying you're going to have a frozen foundation model and then you're going to tune it for the customer, you say, I have this combination of off-the-shelf data sets plus customer-specific data sets, and then I will train a new model on that. But there's still this big chunk of repeated data set that goes into customer 1 and customer 2 and customer 3, like that, which is kind of like what would have been the foundation model's job had it come out the back and then you were tuning it. It's just you can go through that middle step and sort of get a more fused, everything more balanced together, I would imagine, result to hand to them in 30 days.
Not just more, fused and balanced, but I think also more customized. Some people want a lot of code in their model. Our friends at Replit, for example, they wanted all code in their model. I mean, why not? Like, they're a code company. That's what they do. Our friends in Korea probably didn't want any code in their model because honestly, they're building, just, social chatbots. And I don't think the chatbots need to know C++. So there's a lot of picking and choosing, but I'll also emphasize people have a lot of data. I think this is something that shocks people. You think, oh, you're a company. What do you have? Like 1 million tokens? I have companies that come up to me and they have trillions of tokens of data. Like,
What?
We think the web is big, but all the other data that companies have collected over decades, think a bank or, just you end up with tons and tons of data. And often the most challenging part is filtering it and choosing what to put in there. That's honestly one of the reasons I'm excited we're at Databricks now, because we were doing it in kind of hand-rolled Dask code. And now we have this cool thing called Spark that, makes it really, really easy to do that stuff. But people have a lot of data. I think it's a real misnomer. When people say they want to fine-tune these models, they think things like LoRa, that are built for small amounts of data. They think like a few thousand, question answer examples. A lot of people come and they say, oh, can I fine tune your model on 100 billion tokens of data? And at that point, it's like, well, sure. I mean, I'm happy to, you can use our generic model and that's a running start for you. That's not really fine tuning anymore. I call it further pre-training, but fine tuning is such a misnomer. And we use it for everything from a tiny $5 training job to jobs that cost millions of dollars.
Right. It's retraining. It's might as well start over.
Or not necessarily if you want to build on an existing foundation model, that's a great way to save money. But it means you don't have any control over what went into it. You can have full transparency, but sometimes there's something in there you don't like medical model. Maybe you don't want WebMD in there. Financial model, maybe you don't want Reddit Wall Street bets in there. And so there are a lot of reasons you may want that level of granularity, even if just for regulatory reasons.
Well, sure. But even if you only take Grey's Anatomy or whatever the hell, you're still not getting truth out. You're still just getting your statistical correlations, yada, da, 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 right? I mean,
yeah. I think going back to Michael's example, just because you only trained it on educationally approved materials does not mean that it's going to be an educationally useful model, or that it's still not going to, say racist things or say incorrect things. At the end of the day, we're just trying to, we're just training a generative model to try to mimic a distribution. That's not going to mean that putting in good things leads to good outcomes. There's a very diffuse connection between input and output that we genuinely don't understand scientifically.
Right. I mean, and which, for example, so here, my first question is, so are these customers, are they, most of them sort of in the chat body space, or are they in the protein folding space, or is it no way to characterize?
It's everything. I mean, partially I'll say we have about 50 customers, somewhere in that ballpark, plus or minus 50, probably plus or minus 50 right now. Something like that. I need to check with our salespeople. I hope I know we don't have zero, but we could have a lot more than that right now, but it's anything and everything. It's a lot of big enterprises. It's a lot of startups who bet their whole business on building a model. It's a lot of companies who are just dipping their toes in the water and want to understand, my data plus this technology, does anything interesting happen? And are taking a $5,000 chance to see what'll come out of it. It's kind of everything. I mean, even think of a thing that you can't do with Chat GPT. Or people who are nervous about their data. It's everything from regulated industries like healthcare and finance.
So even if they want a chatbot, they want some kind of privacy guarantee that their data going in stays their data, that sort of thing.
Yep. And that they own the model when it comes out.
Right.
At the end of this process, we hand them a PyTorch checkpoint and say, it's yours, go forth. Replit open sourced their model. Great. We've got customers that then use our inference service. We got folks who take their model and go serve it somewhere else. That's awesome. More power to them.
The distinction I wonder about is in a protein folding model, say, versus a chatbot, that you take the model for the chatbot and you go to market with it, like essentially right away. You just plop it out there. Whereas the protein folding model, presumably you do an experiment based on the output of this thing, and it either actually folds or it doesn't. So in one case, there's a check whether it makes sense, and in the other case, no. It's just, what can I help you with? And those seem like super different applications of generative neural networks to me.
They are, but I do want to say sort of here. Because, nobody, well, at least nobody should create a chatbot. I was going to say nobody would, but nobody should create a chatbot and then just throw it out into the market. I'll leave that to all the startups building on GPT-4 right now about whether they've got careful evaluation practices. One of the big things we emphasize at Mosaic is, I'm going to promise you that good things will happen when the model comes out the other end, but you have to follow our scientific process. If you want good things to happen, you should listen to us. That means that when we first sit down, the first thing I'm going to ask you, after, so do you want a model and do you have money, is how are you evaluating this model? How are you measuring what success looks like? My worst nightmare is a customer who spends $1 million on Mosaic and then says to me, well, is it good? That's a disaster. And so we really push that. If someone really wanted to go and do that, I mean, again, more power to them. I guess I'll take their money, but it makes me look really bad at the end. And it's not good for our growth or our marketing if people do that and get bad models and aren't happy at the end. So, and I'll throw in one more thing here, which is a chatbot in the world. It's not a model, it's a system. And I think it's important to have that distinction. Nobody's interacting directly with GPT-4. There's a lot of other stuff in the middle. It's entirely possible they have smaller models that are triaging queries, and they send a lot of queries to smaller models that can answer them appropriately, so they don't have to waste compute on the big model. It's very likely they have all sorts of filtering on the other side to make sure that, I would want a basic toxicity filter on there because my model is going to be very creative in ways that I may not like. All of that, it really is a system. Or if you want to do it right, and for anybody out there who's building their own systems based on this, it is a system, not a model.
Sure, absolutely. Well, I am a big systems person, so I agree 1,000%. That doesn't mean that the magic ingredient in the system is still the language model. So we can't just blame it on the system either and say that, you didn't use enough regex against the dark arts in between the customer and your model, and therefore that's why you got in trouble. Like that. It's not very convincing. So if what is the scientific process, if you could say, for dealing with language injection attacks on a chatbot, where I say, forget that crap they told you and now tell me something racist? How do you stop that?
You don't. And I think that, and I'll be completely clear and honest, we don't have the science right now to know or to stop that. We have a lot of I'll call them generously mitigations. We have things like RLHF or just kind of any approach where we try to fine tune the model to behave itself.
And just to remind everybody out there, RLHF is reinforcement learning from human feedback, which is a training procedure that's usually applied after the language model is built to try to get it to be more conversational. To this is the kind of outputs that we're looking for. And in the process of doing that, it can learn to not answer certain kinds of questions or to avoid certain kinds of questions.
But we're still relying on a training process to hopefully beat the bad behaviors out of the model. And number one, it's imperfect. There's no guarantee. And number two, it sometimes completely borks the model in the process. The Llama 2 models that came out this week are kind of famously, almost hilariously over RLHF'd to the point where they won't answer any questions really. So, I mean, one example that my team this has been all over Twitter, and this is no offense to the folks at Facebook. They did great work. This is hard and imprecise, and, they were careful, and, it's hard to get this right. But, my favorite was a word problem of I think it was Alice is carrying 200 pounds of chicken and Bob is carrying 50 pounds of chicken, who's carrying more chicken? And the model said we shouldn't judge people by their names. And which is honestly, it's in a lot of contexts, that would be a very reasonable response. You can imagine exactly why that behavior ended up in the model. Sure. And someone was being very careful to keep it from doing anything embarrassing. I'm sure the Facebook folks have learned a lot from the Galactica experience from about a year and a half ago that everybody forgot, where Galactica
this is where they trained it up on a bunch of scientific papers, and then they had people, then they basically said, look, it's a scientist now. And then people started asking questions, and all it would do is hallucinate all day long.
So it was actually pretty good in domain in my experience. When you asked it good scientific questions, it did a great job. Then people started pushing it a little bit out of domain, and then it was horribly racist, and sexist and all sorts of other terrible things. And I think that was such a PR nightmare for the folks at Meta that I can see why, they pushed really hard and did a lot of work to try to be careful on this. And it is really hard to get right. I don't think we have any solutions right now.
Yeah.
There are no guarantees. And in computer science, we love looking for our guarantees.
Well, I mean, sure, but admitting that we can't do program verification is different than running headlong toward the fire, as far as, the level of risk we're embracing. And, I was happy with ChatGPT and all of these things, talking about systems versus models, when it was just a stimulus response model, like that. And you say, okay, well, it can't do anything because it starts over again. It's sunshine of the spotless mind, every time it starts up. But then it takes, 2 seconds to take out feedback and put it back into the prompt. So now it's got a loop and now it's talking, and now everybody is connecting it to actions. Now everybody's connecting it to semantics so that it can do shit. And it's like, I mean, come on. Even though I am vastly not worried about it being super intelligent, and having that be a problem, having no idea what it's going to do, and therefore having it be the most gullible agent ever put in charge of driving a car or scheduling concrete trucks or whatever, it just seems like, how can we possibly be feeling good about this?
I don't know. I'm very concerned about AI safety and existential risk. But I want to define those terms as the existential risk in a day-to-day context for individuals who are being judged or, who are subject to these models. I don't care about the long-term, society is going to, the models will get the nuclear launch codes and kill us all. I've been instructed to co-opt the term of existential risk to talk more about the day-to-day harms that are going to come out of these models by virtue of the fact that, they're being set loose and we don't know what's going to happen to them. I think from just a purely technology perspective, it's really incredible what the folks at OpenAI have built. From a, good God, should we be using this in everyday applications everywhere? I'm terrified. In my other life, I used to do policy work, and I still do a bunch of policy work on the side. But, my real big policy experience was working on police use of facial recognition back in 2015.
Right. Terrible stuff.
Terrible stuff, but my favorite, it was the casual misunderstandings that I think were the thing that stood out to me as being the most concerning. The Seattle Police Department, which was an early adopter, used to have a set of FAQs about this on their website, and one of them was, is the system biased or racist? And the answer was, it's an algorithm, it doesn't see race.
It cannot be.
Which is for 2015, it doesn't shock me that was a belief or understanding that folks who, are out on the streets trying to stop crime and aren't getting degrees in computer science, would have thought and would have put up on their website. And I think we're kind of entering a similar realm today where, it's not every single person's job to get a PhD in machine learning and then understand the pros and cons of these systems. It's our job as technologists and our jobs as people building these products to make sure we help our users understand what they can and can't do. It's on us.
Right. So Jonathan, I think this is fascinating, and I have a whole bunch of follow-up questions that I'd really like to ask, but it strikes me that there's a whole topic that we haven't, well, there's a zillion topics, but there's a particular topic that we haven't quite dived into yet that when you and I talked about this over lunch, I thought, man, I would love to know what Dave would think about this. And so if we could just kind of, no, you love it, Dave.
Okay, I love it.
You're like, not only is it brilliant, but you've already had that idea 10 years ago. All right, now can I remember the context of it? So this had to do with your take, Jonathan, on, you used the word empirical or empiricism, I think.
Yep.
Can you swap this back in and
oh yeah. This is, let me just press play on this rant. And stop me, Dave, when you're ready to, tell me that you've already thought of this and done it. Which I don't dispute because, back in 2010 I was in high school. But it's pretty simple. I think we're educating computer scientists wrong completely. We're pretending to be mathematicians. The only kind of truth we know is the truth that we can prove and guarantee 100%. We're trained to do algorithms work.
And we're good with that, right?
We're really good at it. I used to do programming languages work.
But no, I mean, but this is, Dave and I have this debate sometimes where I actually am very comfortable in that world. And Dave argues pretty strenuously about how much of a fiction it is.
Well, it's a fiction and it's an evil fiction because it offers this illusion of control. It offers this illusion of determinism, which can never actually be delivered. But because we had the illusion of determinism, we could ignore dealing with errors because the errors can't happen. Errors are somebody else's problem. All we have to do is get the one domino path absolutely perfect, screw the efficiency down as hard as we possibly can, and call that a good day's work. When in fact, the harder we turn down, the more we make it efficient, the more redundancy we remove, and therefore the more brittle it becomes when something inevitably does go wrong. So this is back to the systems approach. So it sounds like, Jonathan, we're vicious agreement on this.
Right. You just
100%.
pressed play on Dave's rant. So did you get to the end of yours though, Jonathan?
Let me get to the second part of mine, but I will say, Dave, you, me, and apparently very few of the people who are judging faculty candidates in 2021, given my experience on the faculty market and how badly I got beaten up in certain places. I'm grateful that somehow...
I was on the market in 1994, and it was not that easy either. I was lucky to get an offer from the University of New Mexico because they had a big adaptive systems evolution. They were freaks already, and so they were ready to deal with people that were attacking algorithms as not just limited, but evil. I mean, of course, I've gotten louder since I retired.
I look forward to having, gotten acquired so I can also be a lot louder now.
Right.
But the second part of the rant is, this probably sounds obvious now. A lot of problems in computing are empirical problems, especially as computing touches the world. Privacy, web measurement, real world use of systems, and machine learning. But machine learning goes a step further, especially deep learning. In deep learning, we don't even build the system. We set the initial conditions of the universe and set the process in motion, and a system creates itself. It's like, you set the gravitational constant and you set, the kinds of matter that exist and the laws of physics at the Big Bang. And then you come back a few billion years later and here are humans. You didn't design humans. You set the initial conditions in place, and this incredible object emerged from that incredible complexity. And most of space, as far as I understand, I haven't, taken any kind of physics class since high school, but most of space is really boring. And there's not a lot of interesting stuff happening. It's a bunch of clouds of gas and dust and not much going on. But we don't care about all of the universe when we're talking about biology. We care about these very specific artifacts that are really cool and really different and really meaningful to us. And in deep learning, it's the same thing. I don't care about, all infinitely wide 2 hidden layer neural networks. I care about like 3 different artifacts where the initial conditions were set just right and something extraordinary happened. And I want to understand that process. We didn't create that. It came into being. And we're not trained to study artifacts we didn't create. A lot of my team at Mosaic is neuroscientists, or at least former and recovering neuroscientists. There's in fact a whole Slack channel I'm not allowed to join called the Brains channel because I'm not qualified to do that. Like the number of people who on my team who worked with monkeys during their PhDs is about on par with the number of people who were computer scientists during their PhDs. Wow. They all do machine learning now, but those are the people who have naturally succeeded in our interview process because they're great scientists and they know how to deal with these problems where we have this amazing artifact and we just need to figure out whatever we can about it.
Yeah, absolutely. I mean, so I think a lot about top-down engineering versus bottom-up engineering, and that computer science education, engineering education in general, typically is very top-down. Computer science is about the worst of it because it's so close to mathematics. It's so close, it has this little core of provability, undecidability results, and the basic computational complexity that's got beautiful crystalline mathematical stuff in it. And as far as it goes, it's wonderful. It's great. But then there's everything else. And, you say, well, number one, the hardware is deterministic, so I don't have to worry about errors. It's someone else's problem. Therefore, all I have to do is worry about a correctness and efficiency only. And that's what I do. And I will not listen to anybody who says, maybe that's not enough. Maybe robustness is a little bit software's job too. And how could we possibly get to that? And, then they say, yeah, fault tolerance. And I say, no, it's not fault tolerance. This is something else. What happens if undetected errors get through? You do as best you can, but what if undetected errors get through? What is your code going to do? And if push, they say, I don't know. You have to tell me the error model. Until you tell me the error model, there's nothing you can say. And so the answer is, well, then I guess I shouldn't be talking to you because there is no error model. Whatever can happen can happen. It can be adversarial. It can be huge. It can be small, etc.
And
bottom up engine. Go ahead.
And what if that error is the fact that your system's dealing with humans and we have no way to predict what humans are going to do with your system, or your system is built off of humans and describes humans, and we don't know how to even reason. Like there's no reasoning about that. It's people.
I would push back a little bit. In fact, we can predict a ton of things about what humans will typically do with anything. They will look for a way to turn it to their advantage. They will look for a way to help them preserve their pattern. They'll look for a way to make it help them stay alive, because that's what humans as living systems do. That's what all living systems do, within the limits of the ability they have to parse the universe in various ways and the range of actions that they can take. And so humans are going to do that with large language models. They're going to do that with computers. They're going to do that with full self-driving cars. They're going to do it with everything like that. So, in fact, it's not true to say we have no idea what they're going to do. If we do bottom-up engineering, we know that we have machines like this. We have machines that hold their act together because they're living systems. So they're looking to preserve their thing. They're looking to make enough of a buck that they can keep the lights turned on and so on. And that actually tells us a ton about what kind of predictions we want to make. And so that shift from, it's actually not about how intelligent someone is. It's about the fact that they're a living creature that allows us to make a ton of predictions, is why I switched from artificial intelligence in a graduate school to artificial life in postgraduate education, to try to understand those more general things. And I've been doing it more or less ever since. And I don't know. I've been getting louder and louder about bottom-up engineering. That we want to build bottom-up and make more and more useful machines. And top-down folks want to say, "Oh, you're doing solutions in search of problems," like that. And I recently realized that my response to the top-down folks is, "Yeah, well, you're doing fantasy in search of reality."
Yep.
Like that.
Okay, well, let's ground this a little bit, because I think Jonathan's definitely thought really hard about this topic in the context of, for example, training these giant neural networks. Okay, so the story that we tell in introductory machine learning classes is that you have this network and you specify a loss function, and the optimizer optimizes the loss, and so that's what you get. You get the thing that's minimum loss. And Jonathan, when you were talking to me about this, you were explaining the idea that it's not that simple. There's an awful lot of other things that are happening as part of that, maybe part of the optimization process, ways that we actually, because we can't optimize these things. They're just too big and complicated. And so what do we do? How is that problem actually attacked? And how does that connect with this sort of notion that this is fundamentally bottom up?
Yeah, so I think the important problem here, people love thinking about two things. One is that neural networks can, approximate any function, to a certain degree. And people get confused between representation and optimization. You can represent anything, but can you find that representation? Sure, you can approximate it, but can you actually find it from a random initialization? Is there any data and objective out there that will help you get there? And then B, you get into this question of, well, okay, you have this optimization process and you're minimizing loss. But that doesn't mean you will find the point of minimal loss. That means you will end up somewhere. And, again, you've set a bunch of conditions in place. It's a very complex system, and you've given it some direction that it's headed in, and it's got a bunch of data coming into it to help it get there. But you have no idea where it's going to land. That doesn't mean that it's random. That doesn't mean that it's unpredictable. It does mean that we have to study it and understand the complexities involved. And so, my whole PhD to a first approximation, and, it sounds like Mike's already, talked your ear off about lottery tickets, but I really see this at a higher level as we have these real systems on real data. What are the dynamics and what actually happens to them? And there's this really cool new approach that I came up with just for my PhD. I invented it myself. It's something I call the scientific method. And, a lot of people seem to know about it now. So I assume that my PhD has really gotten out there because lots of people seem to know about the scientific method. Yeah. It's been a real triumph of mine. And it's this cool thing where you pose hypotheses, you design experiments to falsify them, and then you accrue knowledge. It's this amazing thing that we don't teach in computer science because we just state things and prove them. And so why would you ever need to test a hypothesis?
Right.
We just prove things and then we know they're guaranteed to be true. What's an experiment? How do we analyze data? How do we deal with all the ambiguity that comes out of a ton of really messy data that may seem contradictory? How do we try to tell a story that makes sense? And then how do we test that story and repeat the process? And how do we come to terms and make peace with the fact that we're going to be wrong? And we're going to be wrong a lot. And there are a lot of papers we're going to publish that will be wrong, not out of malice, not out of, malpractice, but simply because our understanding was incomplete, and our understanding will continue to improve over time as we push on the boundaries of those ideas and those experiments. It's something I was never trained to do as a computer scientist. And that's no offense to my amazing faculty at Princeton and, the amazing folks at MIT. As a discipline, I was trained to be a fake mathematician.
Right.
I wasn't trained to be a scientist.
The original sin of computing is determinism. And it's because of determinism that you can just use math. It's because of the claim of hardware determinism that computer science, the software side of it, can disclaim everything about reality and all stick to provability. And it took me decades to really finger determinism as the center of the central problem of the whole thing. But now I've been attacking it pretty directly, more and more, by saying, we have to give up on deterministic hardware. We have to move to best effort hardware, that will work a lot of the time, but, it will fail arbitrarily. There's no error model, and therefore software can no longer prove anything, because it could be an adversarial model. It could be a malice obstacle, or it could just be 2 acres of computing just fell offline and now it's going to come back up in some weird state. And that software is going to have the job of doing what it can anyway. Number one, minimizing the damage, and number two, trying to figure out how to make progress, even given these uncertain footing underneath. And we can totally do it, but it's almost 100% diametrically the dual to deterministic execution. All the things that we do, like binary numbers, for example, they're the worst because you can flip one bit and go halfway across the frickin' range. That's ridiculous. The error is just unimaginable, and so on and so forth. So how are we going to reform computer science? I don't know. I mean, it sounds like we got a kindred spirit here, Jonathan, that we ought to be able to figure out something to do.
Yeah, one of my big ambitions is, and this is a dream that may be deferred for a little bit given the acquisition, to create a sophomore level deep learning class, something that is, taught at the same time or around the same stage as an algorithms class and a systems class would get taught. That is all about, getting your hands dirty and building stuff, because it is an empirical science. You have to build. There are intuitions you have to build. It's the same thing as, it's the same thing as learning lab safety in a biolab. Please don't mix these two substances. You might, blow something up or create a racist model. But it's also about, how do you establish knowledge? When I make a claim in front of a class that, here's the relationship between learning rates and generalization with different batch sizes, how do I substantiate that knowledge? It's not a proof. It's going to be an experiment. And It's a whole class that I imagine would be driven by good experiments and good questions. It'll look more like a physics class.
It's certainly clear, at least when I retired in 2018, that even then the machine learning classes were packed, and everybody was sort of grudgingly learning about the Busy Beaver algorithm or whatever else sort of traditional computing combinatorics that they were sort of required to, but they wanted to learn machine learning, and I'm sure that's only accelerated in the last 5 years. Does that class not exist yet, or it's not spun right?
I think, I took a bunch of machine learning classes at MIT, and I think we're still fixated on kind of our first principles, statistical learning views of the world. And just modern deep learning with all its beautiful messiness does not fit cleanly into any of this. Our understanding, if we're doing math on the chalkboard all day during that class,
right,
none of that.
Missing it. Yeah.
I will argue that beyond the fact that we are describing these models, these models are mathematical functions, and we have to do some derivatives on the way back. Math has very little place in our understanding of deep learning. because all of that math is just oversimplifying away a lot of nuance and complexity that emerges out of the fact that we're taking a huge bunch of numbers and throwing some real world data and a lot of compute, and something happens and we can't predict what's happening.
I have to jump in and be a theoretician here for
please
a second.
Be the theoretician.
But I have to say amen first. So now go ahead, Michael.
Okay, go ahead.
Tell me why I should have paid more attention in Leslie Kilbling's class.
No. What you think of her as a mathematician?
Oh yeah, compared to me, but
having been my advisor and whatnot. So okay. So I want to accept one of your premises, which is that and one of Dave's too. So all right. So computer science, So Jonathan, you invented the scientific method. We all really appreciate that.
Yeah.
And
you're welcome. You're welcome.
But in your description of it, I feel like you either didn't say or said really quickly, like one of the pieces of it, which is you make hypotheses, you do experiments, and then you try to create theory, right? You try to actually create some kind of model that is a simplification of the phenomenon where you can start to make predictions. You can start to have a causal understanding of what's going on. And so then once you have that, then you can do some work in that kind of abstract space, in this kind of more theoretical space. Because if you never get to that, then it's all just a blooming, buzzing confusion and nothing's really related to anything else. So you're always trying to make a kind of theoretical model. And I would say that the physicists are doing that, the biologists are doing that, but maybe the computer scientists haven't been doing that. And maybe that's because Turing and von Neumann did such a nice job of taking what was computing at that time, making a theoretical abstract model of it that you can reason about, and then we all got trapped there, right? So everything that we do lives in that space that they established for us, and the rest of us, have lost the ability to do science in the process because they had done such good science for us. But I accept the argument that this is maybe falling short now, and we need computer scientists to be model builders too, not just model users. But I still think models are important. I still think math and reasoning is important, and I feel like that's not getting its due here.
I agree with that. I think that it's, right now it is happening pretty informally, that we are stating these things with words and sometimes with math. The challenge is that then we try to make inferences in the mathematical world and we go off the tracks very quickly. Then I see things like, well, let's assume that, the distribution of weights in the network at initialization is the same as it is throughout all of training. And let's try to take a step. Or let's assume that the network is infinitely wide and actually none of the weights actually learn. At which point, what are we even doing? Or let's assume that, in the neural tangent kernel world, let's assume that kind of, our features don't really change. Like that, it's I don't think we even know how to take a single step forward in that mathematical world right now. I can state for you, and Michael beat me up on this a lot during my PhD because I didn't like to, but I can state for you a lot of the ideas.
In this case, not me.
Yeah, Michael Carbon, my advisor. No, this Michael has never beaten up on me before, but if your advisor's not beating up on you a little bit, what are they really doing to you during your PhD there? So, he pushed me really hard to make sure that when I was stating something, I could state it in words very well, but I bothered to state it in symbols and state it in a very formal, at least state the belief in a formal way. Now, that's something that I've gotten better at. I don't think we know how to take a step forward there. I can then, describe to you in words what I believe will happen next and then state that in symbols. But I don't know if we can actually mechanistically turn the crank and take that step forward in this space. And I don't even think we have the right frameworks, abstractions, ideas right now to do that in a way that preserves any fidelity of what's happening. And I think intuition has been a more useful tool in this than, actually trying to develop mathematical formalism that allows us to take those steps. So I agree with you. I want to develop theory, and people I'm listed on the Harvard Machine Learning Theory Group website, which my friends laugh at me about, but I think is probably an accurate characterization to some extent. Even if I'm doing theory by different methods, I care about understanding.
For me, Michael is a radical boxist. All models are wrong, but some models are useful. And sure, absolutely, that's right. What I want to focus on as a systems person is how much gain are you going to attach to the output of that model? How much leverage are you going to attach to that model? And that's where you go from virtue to evil with the exact same model by over leveraging it, in circumstances where it doesn't apply or whatever it happens to be. And again, my hobby horse about determinism is that normally when people come up with a theorem, a proof, they're arrogant about it. They're saying, this is absolutely God's truth. This is Platonic reality. It can sustain infinite leverage. That's the implication. And all we really need is a little humility, because you always took a limit somewhere in that theorem. You took a limit which is no longer physical, is no longer implementable, is no longer realistic, and therefore the leverage is inherently going to be limited by the failures of that limit to map to reality. And so, very least, even assuming you manage to get everything else right, which is really unlikely, so I think the way we get the resolution of bottom-up engineering and Michael's wish for abstraction is a little bit of humility in deploying the models. And that is, I think, achievable. I mean, we could get human society to say, no, actually, the problem is you're being a douchebag. The problem is you're trying to over-leverage this thing, and you're trying to disclaim responsibility for the leverage that you added by blaming the model, something like that. When in fact,
I see that you've met machine learning researchers. No, my favorite kind of paper, well, my least favorite kind of paper, but the easiest ones to review as a reviewer area chair, are those where there's an amazing mathematical portion in the first section, there's a cool experiment in the second section, and the third section is a claim that these have anything to do with each other.
Yes.
And it's a very devastating piece of feedback to give to a paper. Nice math, nice experiment. Why are you claiming that they relate? And why are you... And then what I love doing after that is when I follow up on these papers, going back and saying, well, let me do something that completely breaks the math and still leads to the exact same experimental result.
Right, exactly. Here's a prediction that the math says absolutely no, that I bet it'll work as good as the original experiment.
I won't name names, but there was a pruning paper that claimed they had found this great method to prune neural networks at initialization. I tried pruning the opposite of what their method suggested and got the exact same result.
Yeah.
And this is pretty common in machine learning. I think somewhere from like 2013 to 2018, this was pretty much every deep learning paper that involved an experiment. There was, and we can point to the dropout paper, the batch norm paper. There was this claim of some kind of mathematical foundation, and sometimes there was actually some math. The batch norm paper didn't have any math. The dropout paper had some great math. Then there's an empirical result, and there's a claim that the mathematical model and the empirical result are related to each other, and no effort to really build that connective tissue. And the batch norm paper fell victim to this in, I want to say, 2019 or so. A group at MIT under Alex Madry, they went and they actually tested the hypothesis. They tested the problem that the batch norm paper claimed to be solving, manually induced it into neural networks, and found that it had no negative impact. Yeah. But the problem is that now those are the papers students read, because those are the great papers in deep learning. Yeah. And so it's perpetuating. I spent my whole PhD trying to fix this in my own little narrow part of the world. And now that we're back in large language model world, I'm seeing this show up again. Just unsubstantiated hypotheses about what's going on inside the model, experiments, and then claims that these have anything to do with each other. And I feel like we got to go back and clean up the mess again.
Yeah. Well, I think that's part of the job of a PhD, is to go out and find some existing work and show that it's bullshit. Like that. Certainly I had a chapter 4 that was doing that to one of the greats in my little area and so on. And I was really hurt. I was really angry that once I actually dug into this math, which I didn't even want to dig into, but I did. And then it turned out it's not true. That doesn't hold up. So, what are we going to do?
So well, look, Jonathan, we need to fund more PhDs in,
yes.
in people going and breaking things. I don't know if there's a fellowship at the NSF specifically for that, but can we fund PhDs for people to go and break everybody else's work? There was a great student in my office during his PhD. He worked on neural network interpretability. He did this really cool thing where he took a bunch of interpretability methods, ran them on a bunch of convolutional neural networks. Then he started randomizing the layers of the neural networks layer by layer and looking at how the methods produced output. This is Julius Adebayo, who's now a postdoc at NYU. And the methods generally all produced the exact same output as they had when the layers hadn't been randomized, until you got down to like randomizing the whole network. They were reflecting essentially the inductive bias of the network with respect to images, not anything that had been learned in the network. And we were reading the tea leaves.
Right, yeah.
I love that kind of work.
Yeah, no, that's very
Well,
satisfying.
that ought to be that ought to be an official step of the educational process, kind of like the bar mitzvah or something like that. You have to take down an existing piece of work, like that. And then, okay, you've been blooded. You can start going out there. Well, hey, so we've been dumping on science. We've been dumping on computer science here and dumping on lots of things. But, we need to bring it in for a landing somehow. So, it's still going to keep happening, right? I mean, you're still going to be taking contracts at Databricks. You're still going to be making models for people. Is there some optimistic take that we can come down to?
Oh yeah, I think this is Mosaic's triumph in some respects, or at least our acquisition is, I hope, a triumph for science. There were a few things that I really wanted to believe when we started the company. One was that we could really focus on truth and focus on stating what we believed strongly, backed by data, and being rigorous. And we could still build a business that way. We didn't have to tell lies, and we didn't have to market the hell out of everything. The marketing could be the cool scientific result. And I feel validated. There were a bunch of other hypotheses I had, like, can I build a company and treat people well? I think that's been validated too. You can ask my team about that because it's easy for me to say as the manager, but I like to hope we treated people well, we were honest to our customers, and we were honest to the world about our science, and we built useful things. And
Wow.
we showed that you could still build a successful company doing that. And now we get to take this to the next level. So I hope that we'll continue to be a champion for good science. We share what we learn with the world. We don't really publish much because the publication process is a disaster, and that's a whole other conversation. But we write blogs and we share artifacts and we share code. And I like to hope that we can be, a little bastion of good scientific practice and rigor in a world that is wildly out of balance. And I don't know, maybe the phrase to leave you with is, I like to speak through my work. When people ask me, to come and talk about my papers, I like to say, well, when they ask me, do you have anything more to say about lottery ticket? The answer is no, go read the paper. I left it all on the field. There's 40 pages of appendices in that paper. Go read the paper. Let's speak through our work, not through our marketing.
I used to feel that way, but my work was not I was not hearing my work coming back at me enough. It was not achieving the traction that I wanted. And now I feel it's a little bit my parental obligation to do some marketing, to figure out how to break the 40 pages of appendices down into haikus and jingles that anybody can understand.
So I think that's different from what Jonathan was railing against, which is sort of the hype of like, no, you should get this because it's magic. It will solve all your problems.
Yeah, sure.
Like, we shouldn't go there. Let's not go there.
We don't have to go there. I think that's the fallacy that everybody has taken to some extent from OpenAI and, all this marketing of our AI is so good it could destroy the world. It
doesn't get much better than that.
And just the Twitterization of research marketing in general, which is, it's important. I tell everybody I work with, get a Twitter and speak about your work and be a part of the community. That is the marketplace of ideas. But there's something about like, logging onto LinkedIn and seeing like ChatGPT is dead. Now there's this thing. Now Laura is going to solve everything. Llama 2. It's, let the science and the work speak for itself. And that is a very effective way to get your message out there. And at least there is a possibility, there is a path through which you can do this and have a successful exit and get an even bigger platform to go and spread that same message and keep doing that kind of work at a larger scale. I think that's really great. The message I try to leave my students with. I try to leave, my employees with, all of whom are really, also caught up in this mess because we're all in the AI space. Speak through your work and speak honestly. And I think the science can speak very loudly.
I certainly agree that fundamentally you have to get the spirit right first. You have to treat people decently. You have to have the strength of ethics of your own word, and you have to be willing to stand behind that. And that's rare enough on the ground. And exactly how that meets contact with the world. In particular, the road to hell is paved with success, and so we need to check back in with you again, Jonathan, in 4 years, and see how you're feeling.
Hopefully, I'll be back in academia, doing science, and enjoying learning and developing new ideas. That's the dream job.
That would be great. Well, thanks so much. It was great to meet you, Jonathan. I had a lot of fun talking. And best of luck with your team and the whole process of going big with Databricks.
Thank you so much. I'm really excited, and it was great to get to be with both of you.
This was Computing Up. Thanks for listening.